All right. Nice thing about this equation is that it's a linear equation, right? Linear equation means if you have two solutions, one is called the green y, another solution is called the red y. You add this green y and red y, the green y plus red y is also a solution to the differential equation, right? So a general solution to this differential equation is any function of x minus at plus any other function of g of x plus at. That's the solution to the wave equation. In reality, what you get on the vibrating string is you get waves traveling towards that direction superposed with waves traveling this direction. That's these two solutions. Why? Because if you think of what f of x minus at is, right? F is any function. You draw the function. It is actually the solution at t equal to 0. Like f at t equal to 0, fx is the shape of the function f. Right? When t is equal to 1, the function y is f of x minus 1. Not minus a, sorry, not minus 1. So what is f of x minus a constant? What is the shape of the function fx minus a? Yeah, it's a shifted function, right? Shifted towards the right by this constant a. When t increases to 2, you get shifted by 2a. T is equal to 3, you get shifted by 3a. So it's a function that keeps shifting towards the right. That's what f is. How about g? G is a function that keeps shifting towards the left, right? You get g of x plus a plus 2a, etc. as time advances. So you get two solutions. One goes this way, one goes the other way. So, I mean, you get various interesting stuff. For example, when these two functions coincide in some way, you get vibrations that are seems stationary, right? So basically, by superimposing these two functions, you can see a lot of physical phenomena. Now, the blue equation is exactly the same, except for the solution is not of x and t. It's p of, instead of x, we write z, right? Oh, let me just still write x and z, but is equal to some function g of, instead of x, we have z. Instead of a, we have what? Square root of 1 over m squared minus 1. Instead of t, we have x. Agreed? The same thing. Just a different notation, right? That's a nice thing about math, is that you solve for one equation at some completely different context, you know the solution to another thing. Some f z minus square root of 1 over m squared minus 1 x. Okay. So now, with the interpretation of the string vibration equation, we call sometimes called one-dimensional wave equation, right? In space, how can we interpret these two solutions that's actually in the x and z space? So let's look at f. What does f tell me? Okay. So let's actually draw one of these solutions, z and x. So let's say let's draw f first. F of z minus x divided by the square root of m squared minus 1. Just to make things a bit simple, let's make it let's see what. Just to make things simple, let's say m equal to 2. Okay, so let's say m equal to 2, and well, let's actually stick to the case where we look at the video. Okay, in the video, m is roughly equal to 1.4, right? And a nice thing is m squared is roughly equal to what? 2, right? 1.4 is kind of close to square root of 2. Okay, so that makes things easy because square root of m squared minus 1 is roughly 1, right? So we get f of z minus x. So what does f of z minus x look like in this xz plot? How does the contour of pressure, right, look like when we have a solution like this? Right, contour means like in the xz space we have a fixed value of p at z. What values of x and z guarantees that this is of the same value? Okay, let's say when you're at the origin, right? X is equal to z equal to 0. Okay, you have f of 0. What other values of x and z would you get the same value, f of 0? A straight line, right? So if this guy is about 1, right, then x equal to 1, z equal to 1 would guarantee that z minus x is equal to 0, right? So you also get the same value as x and z equal to 0. So actually, anywhere where x and z are equal, right, x and z cancel out in here and you get f of 0. So the line over which you get f of 0 is this, right? On this line you get f of 0. Right? Any questions on that? Yes?
So if x equals z, wouldn't x over square root of that
Yeah, I'm saying m squared about 2, so square root of m squared minus 1 is about 1, right? Okay. Okay, we're going to see how different Mach numbers is going to affect the shape of the contour pretty soon. All right, so how about a different value, f, let's say minus 1, right? What combination of x and z would give me f of minus 1? Yeah? Yeah, z is equal to 3 or x is equal to 4, right? Or z is equal to 1 and x is equal to 2. Or z is equal to 0, x is equal to 1. Right? So what does that line give me? X is equal to 1, z equal to 0, x2, z1, x3, z2, and x4, z3. That's this line. That's a different value, f1, right? And the contours are just like that, right? You can take different values of different f, right? You see, essentially, on every straight line that goes up 45 degrees, you have the same value of p.